First of all, I want to thank the organizers for inviting me to this meeting. And I will talk about our work with students Scott Gerards, where in some sense we construct designer Hamiltonians, but for different things from what Tribut talked about, designer Hamiltonians for so-called symmetry protected topological phases and symmetry enriched topological phases of bosons. And a theme in my talk is that it's very useful to think in terms of topological defects such as vortices, hedgehogs, and monopoles to understand such topological phases. And so here is outline of my talk. I will give a very brief motivation for studies of such topological phases, and then review thinking in terms of topological defects, and in particular some very useful case of vortices in 2+1 dimensions. And then the main message of this talk is that we can understand some large families of SPT phases as arising from binding topological defects and charges and condensing with composite objects. And then I will describe specifically integer quantum Hall states of bosons in 2+1 dimensions and bosonic topological insulators in 3+1 dimensions. So the broad context is interacting generalizations of topological insulators. So free electronic topological insulators in 2 dimensions and 3 dimensions that brought so much excitement to condensed matter physics in the last decade are phases which are protected by charge conservation and time reversal symmetries. But in the bulk, there are no exotic excitations, but there is something topological about them, and that manifests itself in unusual and robust edge states. And natural question is what happens if we have interactions? And one aspect of the question is whether free electron topological insulators are stable. And another aspect, can strong interactions actually produce new phases which have the same properties, that they have no exotic excitations in the bulk, but are protected, distinct from trivial insulators. And this question is particularly sharp for bosons where there are no non-interacting topological insulators. So everything will be from everything that we can talk about must come from strong interactions. And the foundational works on these are so-called symmetry protected phases are by Van's group, who produced some classification using cohomology approach, and this was very formal, and physics was very beautifully exposed and extended in a series of works by Ashwin, Vishwanath, Senthil, and collaborators. And in this talk, I will talk about this looks. So in this talk, I will describe simple models in 2 and 3 dimensions for SPT of bosons, which realize this physics very explicitly and hopefully demystify some of this beautiful work by Ashwin and Senthil, and particularly in 3 dimensions. And this approach also allows very natural generalization to fractionalized variants of these topological insulators with so-called symmetry enriched topological phases. So throughout, I will use, so for bosons, it's very convenient to work in path integral language. So that's what I will do throughout this talk. So the path integral maps d-dimensional quantum problem to d+1 dimensional stat-mech problem, where the extra dimension is time, and I will use Euclidean path integral language where this is imaginary time. So if we think about the system of bosons, and if we write path integral in the position basis, then we obtain statistical mechanics of word lines of bosons. And if we are on a lattice and this picture of word lines of bosons is essentially the same as developing path integral in the boson number representation. And on the space-time lattice, we will get some statistical mechanics of oriented loops, which you can think of as integer-valued conserved currents which reside on the space, on the links of the space-time lattice. So the prototypical action is where we have some short range or here static energy cost for having this boson space-time currents. And again, throughout, everything will be at integer density. So the simplest action is then just j squared over 2 beta. Beta is some parameter. So of course, we can develop path integral in phase, alternatively in phase representation, and in the phase representation, we would get yeah, the screen is on. Actually, the screen went blank, so maybe it no, is there? But is there some setting to? Yes. Was not the case for you. Display sleep, maybe it's set to, okay. So the path integral in the phase representation is then just statistical mechanics of xy spins. So we have these two-component spins parameterized by phase, and the interaction is just some minus cos grad phi. Okay, so the familiar phases of bosons are superfluid phase, where in the phase language we have just long-range coherence and ordered xy spins. In the boson number language, when phases are ordered, boson numbers are fluctuating, so we have proliferated word lines of bosons. Now, in the Mott insulating phase, on the other hand, the boson number fluctuations are pinned, and we have only small word lines of bosons, while the spins are disordered. And we know that it's actually in the phase language, this transition from superfluid to disordered phase is can be understood as proliferation of vortices, and where this picture is very powerful is in 1+1 dimensions, where, okay, here we do not have true long-range order, but we have a quasi-long-range ordered phase But it is distinct from the disordered phase. In quasi-long-range ordered phase, correlations decay as parallel. In the disordered phase, they decay exponentially. And the disordering transition is driven by proliferation of vortices. So we can re-express 2D XY model completely in terms of vortices, which are long-range interacting points in this 1 plus 1D space-time. And this Coulomb gas of vortices can be analyzed by this beautiful, and the transition is unbinding, vortex-anti-vortex unbinding, and this transition can be analyzed essentially completely by this beautiful real space RG by Kosterlitz-Towles, and can also be analyzed by field theoretic RG, and we know everything about this transition. So one point I want to note here is that the power law correlations, the power law varies continuously in this quasi-long-range ordered phase, and at the transition, the threshold is 1/4 corresponding to minimal stiffness to prevent this vortex-anti-vortex unbinding transition. So of course, the success of Kosterlitz-Towles in this 2D XY model led people to try the same approach in 3D XY model. So here we also can express the problem entirely in terms of vortices. Now vortices become lines. So think of stacking two layers of 2D XY model and keeping track of vortex in each layer, you will get lines. And this, they have long-range interaction of this Biot-Savart type, so vortex current times vortex current divided by R. And we can think of these lines as word lines of quantum particles, so we can think of vortices in 2 plus 1 dimension as particles and describe it by a vortex field. And we can write field theory for this collection of vortices by coupling this vortex field to a dynamical gauge field, and this reproduces these long-range interactions among vortices. Okay? And this mapping can be formalized and made very precise on a lattice by so-called duality transformation. And when doing this transformation, one also can give precise meaning to this dual gauge field. In this notation, the flux of the dual gauge field divided by 2 pi is like coarse-grained boson density. And this is like a hydrodynamic, you can think of this like a hydrodynamic description of the original XY model in terms of some coarse-grained boson densities. Okay. Now, unfortunately, neither thinking in terms of this stat mech of vortex lines, nor thinking about this continuum field theory led to understanding of the 3D XY transition. So in particular, this field theoretic approaches to this field theory failed for this one component problem. They predict first order transition. However, this thinking in terms of vortices proved to be very useful for describing gapped phases of gapped insulators of vortices. So let me just review first simple phases in terms of vortices. So the superfluid phase is the phase where vortices are gapped, and in this field theory, when we can just forget about the vortex field, we get just this gapless photon field, and this photon field is actually precisely the Goldstone mode of the broken U1 symmetry in the superfluid phase. Now, mode insulator we can understand as a condensate of vortices, so this vortex field condenses, and in this case, by Higgs mechanism, there will be actually, in this field theory, there will be no gapless modes left, and this is what we expect in the multi-insulator. Now, the excitations in this Higgs phase are vortices in the vortex field, so they are Abrikosov-Nielsen vortices, and they are objects which have short-range interactions, so these are so-called screened vortices. And the flux quantization, and what we know is that actually these vortices, Abrikosov vortices, they trap precise flux quanta of this gauge field, and the unit is, so if you think of this as Ginzburg-Landau theory for a superconductor, charged superconductor, the unit flux is hc over q in whatever units one has. And here this corresponds, when I used units like this unit flux is 2 pi flux of the gauge field, and this corresponds precisely to charge 1 of the original boson. So this vortex in the vortex field is a lump carrying charge 1, and that's what we naturally expect from direct picture of the multi-insulator. Okay? So now, so far, we have not learned anything new from the vortex perspective, but where it becomes very useful is when we think about unusual exotic phases of bosons, such as fractionalized phases of bosons. So because the power is that these phases, which can be highly non-trivial in the original language, are actually relatively simple in the dual language. So a very famous example where actually Sentil played important role in clarifying is a picture of the Z2 fractionalized phase as condensate of pairs of vortices. So we postulate that we have some phase where pairs of vortices condense, so this is a picture, while single vortices are still gapped. So this phase will be a multi-insulator because the phase of the bosons is scrambled by vortex condensate. Now, excitations in this phase will be vortices in the pair vortex field, and these now trap flux quanta, which is hc over 2 vortex charge, because this pair vortex carries twice vortex charge. So they carry a flux quanta, which is 1/2 of the microscopic unit, and this corresponds to 1/2 of the charge quantum. And this, so where we see that in this phase we have charge fractionalization, and this is not the full story yet. There is one more excitation, which is single vortex, which is still gapped. Now it's a Z2 particle because you can only, in the presence of pair vortex condensate, you can only distinguish even or odd number. And when you have such unpaired vortex, and you take this charge half around it, you pick up a phase pi. And this unpaired vortex is what Sentil called Wison. So now this is full description of the this fractionalized phase. We have charge half charge-on and Wison, and we have mutual statistics of pi. So now I turn to discussing SPT phases of bosons, and I will have pictures in terms of such proliferated objects a little bit later, but let me first proceed a bit algebraically. So so the problem here is that the context here is that there is the cohomology prediction of Z classification of phases of bosons with U1 with only charge conservation, and Ashwin and Yuan-Ming Lu realized that this corresponds to integer quantum Hall states of bosons, and I will provide simple models realizing this. And let me increase, so rather than having single U1 symmetry, let me increase the symmetry to have 2 U1s. This makes analysis simpler, and everything that I will say can actually be made 100% precise. So, so we have two species, or two U1 symmetries. We have two species of separately conserved bosons, and I will use phase representation when describing this system in path integral, and I will use phase representation for the phase species, so U1 phase phi 1, and I will use number representation for the second species. So this is J2 current, which satisfies divergence-less condition. And trivial, it's very simple to construct. Trivial insulator, I will just take mode insulator, decoupled species, and mode insulator in each of them. And in the phase representation for the in the variables that I choose here, so I get XY model for the phi 1, and it's in the small beta parameter regime where its phases are disordered. That's mode insulator of phase species, and model for the second species in the current variables lambda J2 squared. When lambda is large, you have only small loops, so it's mode insulator of the second species in these variables. So now I use these variables because here, when I have phase representation, I can easily define vortices for species 1. So suppose you give me a snapshot of phi 1 in this 2 plus 1D space-time, then I can tell you where we have these vortex lines and represent them by conserved integer-valued vortex currents Q1. And for the second species, I will use the same variables as before, J2. And now I will make the following simple modification of the model from the previous slide, where I will replace this lambda J2 squared term by term lambda J2 minus Q1 squared. Okay? And I claim that this model in the regime of small beta and large lambda is SPT phase of bosons. So what is the physics that we are trying to realize here is binding of vortices of type 1 to charges of type 2. If this lambda term wants the J2 current to be always following the Q1 current, okay? And now if this condition is satisfied, then this term is happy, and this term in the small parameter regime, in the small beta regime, does not penalize these bound objects much, so when this phase realizes condensate of these bound objects. Now, I claim this is SPT phase. How do we know this? So it's actually very simple to see this. In the partition sum, we have integration over phi 1 and summation over J2. And let me make the following change of variables. Go from J2 variables to variables G2, which are J2 minus Q1. Okay? And you see, for each fixed phase configuration, I have fixed vortex configuration. And then as I sum over J2, it's the same as summing over independent G2. And in these variables, my action actually completely decoupled. So from this, we immediately know the phase diagram of this new model. It has these it's just straight lines because it's two decoupled models. And the phase we are interested in is this, in this regime, small beta and large lambda. And picture in terms of original variables Q1 and J2 is that we have proliferated bound states of vortices and charges. And we have very good understanding of these separate pieces. There are no exotic excitations in this phase. Okay? The excitations, for example, what is the meaning of excitations of J2, where the meaning is small loops of G2 are deviations from this perfect binding. Okay? But there are no anyons, no exotic excitations in this phase. Now, how do we know that this is a non-trivial phase? Actually, I claim that this is integer quantum Hall phase of bosons, and to see this, we just need to to couple our bosons to probing fields and just keep track of these probing fields. So, because we have two separate U1s, I introduce two probing fields, A1 coupled to probing the phase boson species, and in the phase representation, this is the minimal coupling. Grad phi is replaced by grad phi minus A1, and A2 is coupled to the current of the second species. And now we can do the same change of variables. So instead of this J2 minus Q1, I will get G2 squared. But now this coupling to A2 external becomes G2 times A2 external plus Q1 times A2 external. And what we want to do at this stage, we want to integrate out all matter field to get effective action in terms of probing fields. Now, we still have decoupled either phi 1 and G2 variables. Integrating out G2 variables will just give me some Maxwell term for A2 external, some renormalization of permeability. Now, so all interesting physics will be contained in this, and what we have here is effectively we have XY model who in the regime where vortices want to proliferate, and vortices are actually effectively carrying charge with respect to second A2. So you can add to the second gauge field. So you can anticipate quantum Hall physics from this fact that vortices are charged. And it's very easy to actually derive quantum Hall response. So this is theory for this XY model in the vortex variables. So in the absence of probing gauge fields, this is the Higgs model I wrote earlier. Now with the probing gauge fields, the way we couple to A1, remember I said that curl of A is coarse-grained boson current, so that's how we couple to A1. And we couple to A2, we say vortices are charged with respect to A2, so coupling is just the minimal coupling of the vortex field to A2. So now we want to study phase where vortices condense, and what happens is by Higgs mechanism, now this object little a plus capital A2 external is what gets gapped. So from this, we conclude that little a is spinned to be minus 2 external, and then we plug it in here, and we get effective action in terms of probing fields, which has this mutual Chern-Simons form. And the meaning of this is if you are applying electric field to drive current of phase, electric field to the first species, it actually drives current in the perpendicular direction of the second species. And if we want to study the original problem I said with single U1, we can imagine introducing tunneling between the species, effectively gluing A1 external to A2 external, and then this action in these units that I use corresponds to even sigma xy equal to integer quantum Hall state of bosons. And that was the prediction of finding of Yang Ming Lu, and there is no time reversal. Yes, there is only U1 symmetry. Time reversal is broken. Yes. So you can actually see where I broke time reversal is where I postulated what plus charge of vortex bound to plus charge, plus vortex bound to plus charge. That's where time reversal is broken. Okay. Now, when we have a quantum Hall response, we expect edge states. And actually, we can, within the same, we can study how these arise in the same model by just modifying this lambda term to now be J2 minus eta Q1, where eta will vary in space. So in one region, I will have eta equal 1, and that's the claimed quantum integer quantum Hall insulator, and in the other region, I will have eta equal 0, and that's the trivial phase. And you see, so this is picture of the quantum Hall insulator is condensate of bound states of vortices and charges, and picture of the trivial insulator is just this condensate of vortices. So vortices of type 1 are present in large loops on both sides, but on one side they are present by themselves, and on the other side they are present bound to charge. And the mismatch in the type of bound states is crudely what gives rise to edge states. And one can actually analyze it in more detail. So let's take the same action, and let's try the same change of variables. So going from J2 to G2, but now I have this space-dependent coefficient in front of Q1. So in this case, when I take divergence of G2, it's actually non-zero because there will be places where I need to differentiate with eta. Now eta is a step function going from 0 on 1 to 1 on one boundary and from 1 to 0 on the other boundary. So the result is that we get delta function on one boundary times, if this boundary is perpendicular to x direction, times vortex current in the x direction, and delta function minus delta function on the other boundary and vortex current in the x direction. Okay. Now, naively, the action is still has phi 1 and G2 decoupled, but actually the two are coupled in the presence of boundary by this constraint. Okay. We can still analyze this in the limit when lambda is very large, deep in the insulator on both sides, deep in the quantum Hall insulator on one side and trivial phase on the other side. In this case, this lambda term will penalize J2, and we can take G2 equals 0 everywhere. And what you see this will give is that we constrain there be no vortex crossing these boundaries. Okay? So if we focus on one surface, away from the surface we have we have disordered phase fluctuations. But near the surface, we have XY model with some parameter plus complete prohibition of vortices. Okay? So this is like, and if we have XY model with prohibited vortices, all we have is spin wave theory left. So when the edge theory is just spin wave theory in this phi 1 variables, we have one gapless non-chiral mode, and this agrees with, again, prediction from Lu and Vishwanath using K-matrix approach. Now, we can actually, something I haven't mentioned yet, look at this model. Actually, even though this model is describing quantum Hall state of bosons, it's actually a classical stat-mac problem with no sign problem. So we can actually study this model also even in the presence with boundaries using classical Monte Carlo. So we can study, for example, boson-boson correlations along the boundary between non-trivial and trivial insulator. And we find indeed that these correlations decay as Pavelo for both species, first species and second. species. And a couple of interesting points to note here. First, note that these are raw data showing power laws, and the slope is the power, and these powers for the two species are summarized in this plot. And first of all, note that this power can be quite large, and actually for one-dimensional bosons, 1 plus 1D bosons, the power could not exceed could not be faster than 1/4. Okay, well, and that's because vortices are allowed, and if the power were faster than 1/4, vortices would proliferate. So here, vortices are effective. This is not a 1 plus 1D system of bosons. This is a boundary of between topological and non-topological phase, and at that boundary, vortices are effectively prohibited by bulk physics. And this power then can be arbitrary, so that's one point. And second point is actually that the powers for the two species have opposite trends, and it's in agreement in that actually in this, if you were to think about dual field to the phi1, the phase field of the second boson species actually happens to be dual field to the first boson species at this boundary. And that's, again, the prediction from K-matrix approach. So now I can very readily generalize this model to produce arbitrary integer quantum Hall insulator. All I need to do is replace this term J2 minus Q1 by J2 minus some integer CQ1. The physics here is I am realizing condensate of bound states of one vortex and multiple charges. And if you go back to the analysis for where I derived sigma xy, all that happens is the same works. All that happens, I will have factor of C here, and I will have sigma xy is 2 times C. So now, again, now we can make actually an interesting different generalization where we will take this term and modify it to read D is some integer J2 minus CQ1 squared. Okay. Now what this now does, it's actually realizing condensation of bound states of D vortices and C charges. Okay? And now I claim that actually this realizes fractionalized version of this 2D bosonic topological insulator. So you can anticipate that this will be fractionalized by the fact that we have condensed objects which have multiple vortices in them. Earlier I described if we condense pair vortices, we have charge 1/2 fractionalization. Here objects which are condensed have d-tupled vortices, so we expect charge 1/d fractionalization. And because this object also have charges, we expect sigma xy response. Okay? Now in this case, there is no simple change of variables which would lead to decoupled systems, unlike the SPT, unlike the integer quantum Hall cases. But actually one can analyze the properties of this phase in the regime lambda and beta in a fully controlled manner, and one indeed finds that there are excitations carrying fractional charge, that sigma xy is 2 times C/d, and these excitations have some mutual statistics which is determined by this parameter C and D. Okay. So this is what we call symmetry enriched topological phase. So the character of the topological phase is essentially the same as ZD toric code, but now the E and M particles or in addition have charge assignments to them. So that's the symmetry enrichment. Okay. So now I turn, and I mentioned that we can, there is no simple change of variables, but actually this model is still has no sign problem, so it can be studied in Monte Carlo. So besides this fractionalized phase, we understand fully deep in the phase, but we can also study broader phase diagrams. So this is an example of such phase diagram where in the fractionalized phase we realize binding of 3 vortices to 1 charge, and there is an interesting, empirically we find that there is an interesting transition from this fractional quantum Hall insulator to trivial insulator, which at least as far as we can tell looks continuous. And the field theory for this transition coming from the fractional quantum Hall state is simultaneous condensation of 2 bosons which have mutual statistics mediated by 2 gauge fields with mutual Chern-Simons. So our models in some way, in some sense, allow studies of these type of phase transitions. So now I turn to 3-dimensional, 3 plus 1 dimensional bosons. So now in 3 dimensions, just having U1 symmetry does not give a non-trivial SPT phase, but having U1 symmetry and time reversal, like in electronic case, gives new SPT phases, and that's what we want to construct. And again, I will enlarge U1 to 2 U1s. I will call the first U1 U1 spin, and the second U1 U1 boson. And the first U1 I will even represent not by planar spins, but I will represent by all 3 spins with easy plane anisotropy. So you will see in a moment why I want to do this. So the Euclidean path integral I will develop in spin representation for the first U1 and current loop representation for the second U1. And you will see very close analogy to what we did for bosons earlier. So the trivial insulator is just the Heisenberg model for the spins in the paramagnetic phase and loop model for the bosons in small loop phase. And now I modify this model to produce a non-trivial phase as follows. When we have all 3 spins and take a slice at fixed time, now we have 3D system. This all 3 spins allow point topological defects, which are hedgehogs. Now in 3 plus 1D space-time, hedgehogs become lines. So I can think of hedgehogs as, in some sense, quantum particles, and these are word lines of hedgehogs. I can describe these word lines by space-time, integer-valued space-time currents of hedgehogs, and there is a unique prescription how to go from n to these currents of hedgehogs. And now I modify the previous model, just like we did in 2 plus 1D. I replace this lambda term by term lambda j minus q squared. And the idea is what we are realizing here is binding of bosons and hedgehogs excitations. Okay, so just like just like we argued in 2 plus 1D, this phase has no unusual excitations. The same change of variables goes through. Again, the phase we are interested in is this phase at large lambda and small beta, where in some sense we have proliferated objects which are bound states of hedgehogs and currents. Now there is a distinction between this construction in 3+1D and 2+1D, in that actually for this to be a new phase in 3+1D, we need to require an additional symmetry. So specifically, our model has such additional symmetries. So for example, our model has symmetry where I change NZ component of these spins to be minus NZ. What this does is it reverses, changes the sign of the hedgehog, and I can, the model is invariant if I simultaneously change the sign of the boson current. Okay. Now, what happens if we do not have such additional discrete symmetries is that actually we can, for example, if we do not have this symmetry, we could add Zeeman field on the spins, okay? And then model with eta equal 1, where I claimed this binding of charges and hedgehogs, can, in the presence of Zeeman field, can actually be continuously connected to model with eta equals 0. The argument is actually very simple. Let's start with eta equal 1. And even in the presence of Zeeman field, we can change variables to this N and G decoupled systems. Now, spins are paramagnetic. This is some field on the spins. I can increase it from 0 to infinity without undergoing any transitions. Now, at very large field, actually spins are aligned. There are no hedgehogs. And when there are no hedgehogs, it doesn't really matter whether eta is equal 1 or 0 here. I can then at that point move eta from 1 to 0 without undergoing phase transition. And then I bring field back down to 0. And I made, if I allow Zeeman field, I have a connection without phase transitions between these 2 points. Okay? But this path is not allowed in the presence of this time reversal symmetry. And the difference from bosons in 2+1D is in some sense that hedgehogs for all three spins is not the full story, like while vortices for U1 spins is a full story. Okay? So another point here, again, distinction from the boson SPTs in 2+1D is that in this boson quantum Hall state, if you take 2 copies and add them together, you get a new boson quantum Hall state with twice as much sigma xy. Here, if you take a model with eta equal 2, you can again construct a path now without breaking any symmetry to model with eta equals 0 without ever undergoing a phase transition. I will not give details of this, but okay. Now, unfortunately, so in how does one show? So suppose we have U1 and this additional discrete symmetry. How does one show that it's a non-trivial phase? Unfortunately, we do not have such simple argument like in 2+1D where I just calculated. I showed you that it has quantized sigma xy. So what we can do is, following Ashwin and Senthil, is argue for the non-triviality of this phase by showing that boundary of this phase realizes something which cannot happen by itself in 2 dimensions. Okay? And before I discuss that, let me actually give you this useful picture of hedgehogs for easy plane spins. So when we have only U1 symmetry, actually topological defects are vortices, and in 3+1 dimensions, in 3 dimensions, vortices are lines. But if we had hard planar spins, when at a vortex, the spin doesn't know what to do. Okay, but if we have all 3 spins, so the vortex is a singularity. But if we have all 3 spins, the spin can actually escape in the core of the vortex. It can escape out of the plane. Okay, But now it can escape either in the plus z direction or in the minus z direction. So in this context, we naturally have two different cores of WOV. We can speak of cores of two types, one with spins in the plus z direction and one with spins in the minus z direction. And consider such a vortex where the core type changes somewhere along the vortex from down spin to up spin. And if you look at this picture, this is actually the same as hedgehog. Okay? So now here there is actually some correlation between if in the same between the sign of the hedgehog and there is precise correlation between the sign of the hedgehog and from which type to which we go. So here I went from downspin below to upspin above, and the sign of the hedgehog is plus. If I take the same vorticity, but the core here is up while here is down, it's minus hedgehog. Okay? Or if I keep the core unchanged but change the sign of the vorticity, again I change the hedgehog number. Okay? So now, so what I want to consider next, what I want to argue next is what Ashwin and Senthil proposed, is that on the surface of such three-dimensional bosonic SPT, if you break time reversal, you will realize quantum Hall state with sigma equal 1, which for bosons is not allowed in 2 dimensions. Okay. Now, I can argue for this as follows. Let me think not about a single surface, but let me imagine a slab. So I have 2 surfaces. And let me break time reversal by hand on both surfaces by applying Zeeman field in plus direction on one surface and in minus direction on the other surface. So what this will do is it will effectively, if the Zeeman field is large enough, it will effectively prohibit vortices with down core crossing the top surface and up core crossing the bottom surface. And what in this case, if you look at these pictures as far as what kind of vortices are allowed, we always require up core on the top surface and down core on the bottom surface. And then there is a definite correlation between vorticity and the hedgehog number. If vorticity is plus, the hedgehog number is plus. If vorticity is minus, the hedgehog number is minus. This is not true if I did not have the Zeeman field, okay? Because for these vortices that I prohibited, here the relation between vorticities and hedgehog was opposite. So now, in this slab geometry and in this deep in this parameter regime where we condensed, now I add physics that we bound the charge energetics of binding charges to the hedgehogs, and what this realizes, this slab realizes, is actually integer quantum Hall state of bosons like I described before. Condensation of bound states of charges and vortices with definite relation, plus charge bound to plus vortex, minus charge bound to minus vortex. So the slabs of this SPT phase has sigma xy equal 2. Half of it comes from the top surface and half of it comes from the bottom surface. This is actually analogous to, and even this argument is analogous to a very familiar statement. If you take three-dimensional topological insulators, in the presence of time reversal, you have single Dirac cone. But if you break time reversal on the surface, for example, by depositing ferromagnet, you gap out single Dirac cone, and you get sigma xy equal 1/2. So this is boson SPT version of the same physics. Okay. Now, we can actually describe also physics at the surface more generally in the so the previous example was where I broke explicitly time reversal on the surface. So let's not do that. Let's maintain time reversal in the model. We can study a boundary between this non-trivial insulator and trivial insulator, just like I did for the 2+1D case, by taking this binding term to have eta, which is 1 in one region, so this is the non-trivial phase, and is 0 in the other region. And again, the interesting physics on the boundary is because of this mismatch. And one can analyze this physics, approach this physics by similar analysis as we did in 2 dimensions. So again, let's try this change of variables from J to G. And again, this led to decoupling if we just had topological phase. But in the presence of the boundary, we have actually an additional constraint that divergence G is delta function times hedgehog current across the boundary and minus delta function hedgehog current at the other boundary. Okay? And again, in the regime of very large lambda, so now these n's and g's are coupled, but in the regime of very large lambda, we expect g's to be essentially 0 everywhere. And then focusing on a single surface, what we effectively have is O3 spin model with complete prohibition of hedgehogs. Okay? And this model was already mentioned in Rebus talk, and it has some history, starting with work by Lau and Dasgupta and Kamal Murphy. And with Ashwin, we argued that the one way to understand the physics of this hedgehog suppressed O3 sigma model is by this NC-CP1 field theory, where we have CP1 field coupled to a non-compact gauge field. Okay, and this is where this statement I made earlier that hedgehogs is not the full story for free spins becomes very that statement becomes very precise. Okay, so now actually we can also keep track of coupling to the probing field. So imagine a U1 field probing the first U1 and a U2 field probing the second U1. In this NCCP1 model approach, we represented spins by using 2-component complex field, so Z up and Z down. Each can be thought as carrying 1/2 of the original U1 charge. So in the field theory, Z up will carries plus 1/2 charge, and Z down carries minus 1/2 charge. And the non-trivial result that coming from carefully going through this change of variables is that the flux, this gauge flux of this NCCP1 field theory actually becomes charged with respect to A2 external. Okay, so and this is actually field theory for the surface that Ashwin and Senthil just said, and God said, this is the field theory. And here we can actually, in some way, we have a microscopic derivation of this field theory. And from this field theory, one can understand by very simple arguments all possible phases on this surface. so the surface theory is this is the surface theory which contains different phases. There can be different phases in this theory. Actually, so actually, so that phase again, it's not contained in this simplest theory, but this theory can be also coerced. So Ashwin and Senthil discussed there is such a phase which does not break any symmetry, but it necessarily has intrinsic topological order. And so in the previous transparency, so in this specific model, actually it will break all free symmetry. Yeah, it's not crucial. In this model, in this specific model, it will break. So this is this work, Lau and Dasgupta. They tried complete prohibition of hedgehogs on the cubic lattice, and they find only ordered phase. So if I take this specific model and realize the surface like this, actually it will break the first U1 symmetry. Yeah. So actually we have. If I have two U1s, this is actually surface phase diagram in a generalization of that model, and we have both. So this is the phase with broken symmetry, and here this is what with broken first U1 spin symmetry. This is the photon phase. The first U1 symmetry is not broken, but actually the meaning of the photon is Goldstone mode of the broken second U1 symmetry. So we have a generalization of this model where we actually see all different, we have phase diagram for the surface, and we in the simplest model, we have only symmetry phases which break symmetry, either one or the other or both. Okay, but yeah. So if it's U1, it will again be broken U1. If I take all three spins but with easy plane, it will be yes. Yes. So okay, if I will, so if I have separate U1s, it's a little bit richer than single U1. If I now try to glue with separate U1s, there will be no distinction between these.
There is, in principle, a boundary that doesn't break anything. That doesn't break the U1, so the SVP phase is fractionalized. That comes back. Yeah, and he doesn't realize that.
Yeah, no, not in this simplest theory. It does not appear in this. Yeah.
I think we should let him finish. And yes.
Okay,
well,
so
you're out of time actually.
Okay. So just last slide is just like we did in 2+1D, we can actually realize fractionalized versions of these bosonic topological insulators by realizing, again, the physics, the idea is you now condense bound states containing multiple hedgehogs and charges. And this is a fractionalized phase. The topological order is Zn toric code in 3+1 dimension, but there is the symmetry enrichment, and in particular, it has fractional specific prediction for fractional Witten effect. So let me stop here.
Thank you. So maybe one or two very quick questions with very quick answers.
Just to understand, in the non-interacting case, I can have a surface that is gapless and doesn't break any symmetries. But it sounds like here you're saying that at least in this model, the choices are break symmetry or have topological order. And either way, it's gapped. Or is there just a simple gapless surface that doesn't break any symmetries?
Not in this case.
And is that a general statement about the bulk phase, or is it just about the model? I mean, this realization is maybe
you can think of this as analog of single Dirac-Kohn theory.
The single Dirac-Kohn theory is gapless.
Well, but it's a theory of electrons, and this is theory of bosons. So this is the, just like that sigma xy equal 1 is analog of.
So this has a point at least that is a gapless.
So
is it a photon or a Klein-Gordon boson?
Presumably, some of this this phase transition could be in this this easy plane NCCP1 continuous if such continuous transition exists.
But you have to kind of fine-tune parameters to get there. It's not a matter of.
Yes, and Senthil has comments.
I think we'll break for lunch here. I mean, there is a discussion session after 2 where all of this can happen. So this is the end of the session. Let's thank all the speakers.